Alright, so let's first start with yesterday's exit ticket. So we have an object that's projected vertically upward from ground level. It rises to a height, maximum height h, if air resistance is negligible, which of the following must be true when it is at a height of half of h. So I'm going to draw a couple pictures, first at the beginning when it's first shot up, and then at the middle when it's like still obviously moving up, but not as fast, and then at the very end, which is from the maximum height. Here, this would be only h over 2, and then this one is on the ground. At this point, see how your potential energy is actually 0, so it's all kinetic energy at the beginning. Here, it would be half kinetic energy and half potential energy because it's halfway. Half the height would be half the potential, and then it still has to total the same. And then up here, it would be all potential energy, and KE would be 0 because it's not moving anymore. Velocity would be 0 at the top. It's at the maximum height, all potential. So most people, they got this wrong, put C. You said its potential energy is half of its initial potential energy. It is half potential energy, but it's half of the maximum potential energy. Initial means beginning. At the beginning, your potential energy was 0. So that doesn't make sense because if it was half of the beginning, then it would still be 0, right? Half of 0 is 0. It's half of the end potential energy, which is not the same thing. So what was true is that its kinetic energy is half of its initial kinetic energy because this is like your initial point, right, at the beginning. I had all kinetic energy, and at this point, it's half of what I had at the beginning. So B, its kinetic is half of its initial kinetic. Here, so which is true about the following. So they both start at the same height, and they both end at the same height. What's different is the path that they took. But if we were to calculate this end velocity using just energy, right, it starts with potential energy at the bottom, or at the top, and then at the bottom it's all kinetic. So your potential energy would be mgh here. There would be no kinetic energy at the beginning because it says they drop from the same height. They drop, so assuming they start from rest, if they're just dropping. And then that would go all into kinetic energy, 1/2 mv squared. So if these two are equal to each other, what you'll notice is that the masses cancel out, so it doesn't matter which one's heavier. And then your velocity would just be 2h equals v squared. So then your velocity is the square root of 2gh. This one has the same g, assuming it's still on Earth or on the same planet, and it has the exact same h, so they would both have the exact same velocity. It doesn't matter the path that they take, as long as you are changing the same height and you start, both of them start from rest, then they both will end with the same velocity once they've gone down h. So they would have the exact same velocity. 3, the roller coaster's potential energy and total mechanical energy are plotted to the right. Which one shows their kinetic energy? So first of all, here I have lots of potential, which means I have very little kinetic, so you can cross off C and D, which everybody did. Now it's just figuring out which one of these matches this one. So I like to look, a lot of you looked at like this point and this point, which is good, but then both of those work out, right? They both have 0 at the beginning and all kinetic at the end. So let's look at a point like right here. So right here, it has very, very little potential energy, which means it needs to have lots of potential energy at this point. So I go over here, I need lots of potential energy right here. Whereas if I look right here, that is not enough to keep this plus this to keep the same total energy. So it had to be B, because this right here at the end, if it has very little potential, all this part, then it needs lots of kinetic, all of this part. And 4, using the graph, which the following is true, actually nobody missed this. The object would be at rest here because this is all potential energy, no kinetic, which means no velocity. It's at rest. Alright, today, so first of all, try this on your own before you watch the video of me going through it. So what we have is we've got a roller coaster ride in Music Park. It lifts a car mass 700 to a point A, which has a height of 90 meters. And the car starts from rest at point A, so right here, this is all potential energy, no kinetics. It says it starts from rest at point A, and it rolls down with negligible friction, that's good, and follows around a loop, blah, blah, blah. At point B, the highest point in the loop, this is 50 meters. indicate on the figure the point P at which the maximum speed is attained. Let's think about it. Starts with all potential energy. Your maximum speed is going to be where kinetic energy is the most. Kinetic energy is the most where you're not wasting any of your energy on potential. So that would be at the very, very bottom. So this would be point P where it's moving the fastest. And then it asked me to actually calculate the value, that's supposed to be max, of the maximum speed. So let's think about, we're using conservation of energy. So that means we're talking about from point A and then it's going to point P. So the energy at A we said was all potential energy, so mgh. And then at P, this is all kinetic energy because your potential is 0 because there is no height, it's like on the ground. So then mgh here would turn into all kinetic energy, 1/2 mv squared. And then now we actually plug in, our mass is 700, g, you can just use 10. At A, our height was 90 meters. And then at P, 1/2, mass is still 700, and I'm looking for velocity. Assuming you guys can solve that on your own. Oh, I think my answer came. And you guys should be getting that your velocity is 42.43 when you rearrange this. So the maximum velocity is 42.43 meters per second. Now calculating the speed of the car at B. So first you should be asking yourself, is this going to be faster or slower than this one? You should have said slower because now the energy, part of the energy is in potential energy. So it's sharing its energy with part kinetic, part potential. So where it was all kinetic, that would be the fastest. It's going to slow down because some of that kinetic is going to go to potential here. If we want to calculate the speed at point B, well, we're still using the same conservation of energy. So you can either say energy at A goes to energy at B, or you can use P to B. It's the same thing. I'll use A, goes to energy at B. So A we already used was the 700 times 10 times 90. Now at B, it has both kinetic energy and it has potential because it has a height and it's still moving. So then we would just do mgh, 710. This height is 50 plus its kinetic energy, 1/2 mass v squared. And again, let you guys solve that. Pause the video while you solve. You should be getting your velocity is 28.28 meters per second, which at least is slower than the maximum velocity, so at least that checks out. C, we want to draw and label the forces on the car when it's upside down. So this is like a throwback to last unit. So first of all, we would have the weight of the car, which of course points down. So I'll just call that Fg. And then the other force we would feel, or the car would feel, is the force of the track on the car. And because the car is upside down and the track is around like this, the track would be pushing down on the car. So that would be the normal force from the track on the car. So it would be both normal and the gravity force pointing down on the car. Now we want to calculate the magnitude of all the forces in part C. Well, Fg is easy because it's just mass times gravity. So this Fg is going to be 7,000 newtons. And then the normal force is going to be a little bit harder because we don't have an equation to find normal force. But we do know the speed that it was going as it was traveling in this loop. And because we know the speed and it's traveling in a circle, that means we can find the centripetal force. So in this case, the two of them add up to the centripetal force. Remember, centripetal force is like your net force just for something moving in a circle. So I'm going to write that my centripetal force is the two of these together. Centripetal force is just mv squared over r is Fn plus mg, the Fg. And now we just plug in. Mass is 700. Velocity at this point, so we're looking for the normal force at this point, was 28.28 squared over the radius was 20 equals normal force, what I'm looking for, plus the mg, which I had already just found, is 7,000. Now pause while you guys solve for this. You should be getting 21,000 newtons. because the normal force plus the force of gravity, both these forces down, add up to the centripetal force with the mass of 700 and this velocity at a radius of 20. Now suppose that friction is not negligible. Negligible meaning it's so small that you can ignore it. Now it's not so small that we can ignore it. Now it actually is going to make an effect. How could the loop be modified to still maintain the exact same speed at the top of the loop? So I want to keep the same kinetic energy, assuming we're keeping the same cart. So I want to keep the same speed, which means I need to keep the same kinetic energy. But if friction is not negligible, that means we're like losing energy. Technically, it's not being lost. It's just going into heat. Friction, think about like when you have friction that creates heat. So we're losing energy in the sense that it's not potential or kinetic energy, but it doesn't just disappear. It goes into the form of heat. But for us, mechanical energy is just potential and kinetic, so we're losing that mechanical energy due to friction. So if I'm losing some of that energy, but I still need to keep the same kinetic energy at the top, then the way we can do that is just make the loop lower down, because then I have less potential energy. So then even though my total might have decreased, well, I'm not wasting some of that energy on potential. It can still stay at the kinetic. So what I would say is you lower the loop closer to ground, because then there is less potential energy. So if energy is lost to friction, meaning it's lost to like heat energy, then can still keep the same kinetic energy, so have the same speed at the top, which is what it asks us to. So now, yesterday we were talking about no friction loss at all. Now we're going to do a couple problems where there are energy losses due to friction, or heat loss. It's the same thing. In this case, we've got a block of known mass, and it goes from position 1 up to position 2 as shown. And the speeds at position 1 and 2 are known. So I know the velocity at 1 and I know the velocity at 2. Describe as to another student at your level of physics how you could show evidence for whether there is measurable friction between the surface and the block. So if you know the mass, you know the velocity here, you know the velocity here, and you know these distances, I want you to come up with some way to prove that there is friction. So definitely pause and think through this part. Don't just play the video. If you want to talk with a friend to think through it, great. Now the answer, and there's a couple ways you could do this, but I think the easiest way is to actually use this velocity to find the kinetic energy. So I would say use the velocity at position 1 to calculate kinetic energy at position 1. And because this one is all kinetic energy, I'll just say UG is 0 here. All we would need to do is calculate kinetic energy. It tells me that I know the velocity here and I know the mass, so that would be an easy 1/2 mv1 squared would be my kinetic energy at 1. I'll just use the subscript 1 to say at this position. And then we also would need to know the velocity here to calculate the kinetic energy here, but this has both kinetic energy and potential energy at this point, because I've gone up some height, but I'm also still moving. So now we would use V2 and we would use the XD, which is the height, to find KE and UG at position 2. And then it would just be, my energy would be the 1/2 mv2 squared plus that potential energy that I just gained, which is mg, and the height in this case is xd. And then we would compare these two values. So if I start with some energy, in this case it's all kinetic, and then I end with some energy, well, if these two are the same, then yeah, I didn't lose any. And if there was measurable friction, then this one would end up with less, because I would technically be losing some of my mechanical energy into friction. So if 1/2 mv2 squared plus mgxd is less than the kinetic energy at the beginning, the 1/2 mv1 squared, then you lost energy to friction. So basically you're just saying, okay, use the velocity, find this energy, use the velocity and the height, find this energy. If this is less, then you lost energy. Pretty straightforward. Number 2, so we have a cart of 30 kilograms released from rest. To follow the path shown, how much energy was lost to heat? So this is a case where there must have been friction. So let's think, at the top it said release from rest. This is all UG. So your UG would be mass, gravity, height. Mass was 30, gravity's 10. The height in this case was 20 meters. So that gives me 6,000 joules is my potential energy at the beginning. So we'll just say this is 6,000. Now, once you hit the ground, your potential energy is 0 because your height is 0. Kinetic energy, normally we would say, oh, my kinetic energy is 6,000, but this is a case where we did lose energy. So we can assume that we have a less kinetic energy than potential because we lost some of it. Now, I actually gave you the velocity, so you can just do 1/2 mv squared, 1/2 3016 squared, gives me a kinetic energy of 3,840 joules. And then it's pretty easy to say, okay, well, if there was no friction, that should have been 6,000. So if I start with 6,000 and I end with 3,840, then how much did you lose? Well, you just subtract, so that means you lost 2,160 joules to heat or friction. Now, some of you might be saying, wait, but your total energy has to stay the same. Yes, your total energy does. In this case, that total energy includes the heat energy that was lost when the friction between the surfaces was, like, when there was friction between the two surfaces rubbing. So it didn't disappear, it just went into heat, whereas before, like yesterday, we were assuming there was no friction, so it would go all into kinetic. It would only be between potential and kinetic, whereas now we are taking into account heat or friction. Number 3, a 250 kilogram roller coaster passes point A at 12 meters per second. If this much energy is converted into heat, so this is like the lost heat energy, what is its speed at B? So first let's find the energy at the beginning. So the top we have potential energy and we have kinetic because it has a height and it's moving. So that's mgh plus 1/2 mv squared, 250, 10. Hopefully you tried this before you watching the video. So we get that your potential energy is 45,000 and my kinetic energy is 18,000. So that means the energy at the beginning, or my total energy, is 63,000. So this is my total energy. Now at this point, point B, oh, you can't see. All the way on the ground, my gravitational potential energy is 0 because I have no height. Now, if there was no friction, then my kinetic should be just the 63,000, but it said that I lost 8,500 joules to heat, so then that means I take away 8,500, and then that leaves me with 63,000 minus, oh, nope, we're good. So 54,500 would be my kinetic energy. Now what I wanted was the speed, so you can just say, okay, well my kinetic energy is 1/2 mv squared, 54,500 is 1/2 mass v squared. You guys rearrange. You should be getting 20.88 is your velocity here, which is slower than if there had been no kinetic energy or no friction loss, because if there was no friction loss, then your kinetic energy would just be the total right here, in which case the velocity would have been 22 point something. So I lost some of that kinetic energy, which means it's going a little slower than if there was no friction. sketching graphs of potential and kinetic and total energy. So the first one, a ball is just dropped from the top of a cliff. So first of all, time, this is potential energy, kinetic energy, time. Sometimes you'll see it as PE, most often you see it as UG, U meaning potential energy, G just saying it's gravitational potential energy, because technically there are other types. Which we'll get into later in the week. And then this one is your total energy, sometimes also called mechanical energy. Alright, so first a ball is dropped from the top of a cliff. So if you want, if it helps, draw a picture. So dropped means that your V naught is 0 and then it falls down like this. So that means I'm starting with some potential energy and then I'm ending with no potential energy. By the time it hits the ground, the height is 0, so no potential. Now, some of you might be tempted to draw a straight line, but if you think about it, this is time on the x-axis, and it does not fall at a constant rate. In fact, it accelerates. So that means that the height would be changing at a faster rate, like more height per second, so at the end it should be steeper. So I'm going to start like this, and then get it steeper towards the end. And we can go ahead and write why this is getting steeper. It says get steeper because it accelerates as it falls. So at the end, it's losing more height per second than it was at the beginning. And then your kinetic energy, well, if it was dropped, you start with 0 kinetic energy. And then obviously it is getting faster, so your kinetic energy should be increasing. And again, it is not a straight line. It is going to be a curved line because increasing at a faster rate, like this. And your energy, kinetic energy at the end is exactly the potential energy that you started with, which is your total energy throughout the thing. And these should be, it's not a perfect diagram, but they should be exact flips of each other, because at every single point, the potential plus the kinetic at that point has to add to the total, or the mechanical energy. Again, this is no friction or air resistance, so no loss. We're assuming that it's all either gravitational potential or kinetic. Next case is a ball that's thrown straight up from the top of a cliff. So instead of just release, now it has some initial velocity up. And then if it obviously has initial velocity up, it's going to go up for a while before it falls back down. So think through your potential energy sketching this. Try these before you watch the answer. So important thing here is that because I threw it straight up, my potential energy, I don't start with the maximum potential energy. I obviously start with some potential energy because it's on a cliff, so there was obviously some height, but my potential energy is going to increase before it falls back down because I go up before decreasing the potential energy, and it's going to be curved because it's accelerating the whole time, accelerating at a rate of negative 9.8 or negative 10 we're going to use. So it doesn't go up at a constant velocity. It's slowing as it goes up and then getting steeper, increasing as it falls down. Remember, your potential energy graph is literally just the graph of the height because it's mass times 10 times the height. So this is what the vertical displacement graph would also look like. All right, kinetic energy. So the important thing here is because it was thrown at the beginning, it starts with some kinetic energy. So let's say it starts like this. And then at the top, the velocity at the very, very top is going to be 0. So on its way up, it slows, so something like this, slows. And then on its way down, it's getting faster and faster and faster. It's accelerating, so now it's going to increase. And its kinetic energy at the end is going to be equal to the very maximum potential energy, the potential energy at the top. Notice that it's greater than the potential energy at the beginning because at the beginning you had both kinetic and potential. Now it's all kinetic, so it'll end somewhere up here. And then my mechanical energy is going to be whatever the total was the entire time. And then we can make a note and say that this system has more mechanical energy or more total energy than above, because instead of just dropping, I started with that same potential energy, assuming it's the same cliff, and I had kinetic energy. So I had more energy to begin with, so I had more energy throughout. The next one, a ball is now thrown straight down. So again, I am starting with potential and kinetic energy. In this case, because it's going down, I'm not going to increase potential energy at any point. It's just decreasing. It's just going to be decreasing at a super fast rate because instead of starting from rest and going slowly and then accelerating, I start with the velocity and continue to accelerate. So I would say maybe something like this, just because it's going to fall down in less time. Again, this is my potential and time. Important here, because I started with the velocity, that means I started with some kinetic energy, and it, again, just increased. And you'll notice that the kinetic energy I'm ending with is more than the potential energy I started with, because I started with both kinetic and potential, so they add up to a greater total. And then my total energy is the two of them together, so the max kinetic would just be my total from the whole time. And a ball is thrown horizontally from a cliff. So in this case, something like this. So because it's thrown horizontally, that affects my energy, but it doesn't affect the time it takes to fall down or if it goes up or down, because X and Y are separate. Think of our projectile unit. So my potential energy graph is actually the same as if it was just dropped. It just happens to be moving along to the side as it was dropped, but the height is changing at the same rate as if it was just dropped. So my potential energy would look something like this. Just like the first situation. My kinetic energy would not look the same because I start with some kinetic energy. I have some sideways motion. So I'm going to start with kinetic energy, and then it's changing, right? It's increasing by the same amount that the potential is decreasing. So that means that my kinetic energy at the end is going to be more than the most potential energy, because the most potential had kinetic as well. And then my total energy is this together, maximum energy. Number one, when you drop a pebble from a height h, it reaches the ground with a speed v if there is no air resistance. What height would you want to drop it so that it reaches the ground with twice the speed? So it helps to draw a picture. Think about, you drop a pebble, so that means it's all UG, there's no kinetic energy because I dropped it. And then no air resistance, so when it hits the ground down here, well, UG is 0 because it's on the ground, so that means it's all kinetic energy. So if you think about your equation, I start with potential and I end with all kinetic, so mgh goes into 1/2 mv squared, so the masses are going to cancel out. And then if I want to have twice the speed, let's think about if you were to plug in a 2v here, well, v gets squared, so really that's a factor of 4, which means that the height would have to be a factor of 4. Another way is you could actually move everything and solve for v, rearrange, so multiply the 2 up, 2gh is v squared, which means that the square root of 2gh is your velocity. Well, if I want to have twice the speed would need to be a 4 in here, because when it gets square rooted, that would be a factor of 2. Or you can make up a height and try it. A rock is thrown straight up from the surface of the earth, which the following describes the energy. So if I throw a rock up on its way up, it's going to be getting slower, which means the kinetic energy is decreasing. Obviously it's going higher, which means the potential energy is increasing, because potential depends on the height. And that makes sense, because if your potential goes up, the kinetic must go down, and the total energy would stay the same. So kinetic energy decreases and potential increases E. Now 3, a rocket is launched straight up from the surface of the earth and accelerates up. Which of the following statements describes the energy transformation of the rocket as it rises? So this one is a little bit different, because it says that it's going up, which means getting higher, so my potential energy increases. And it also says that it's accelerating up, which means it's getting faster. If it's getting faster, that means my kinetic energy must be increasing. Now the only way that my potential and my kinetic can both be increasing, that means my total energy is increasing. So if my total energy is increasing, that means there must be something that's putting energy into the system, in which case there's engines on the rocket. So in this case, it's okay that the total energy is increasing, because there is some outside like force or engine putting energy into the system. So here, both the potential and the total energy increase. So this one, the total energy is increasing because the rocket's engines are doing work and putting energy into the rocket. And we'll talk more about like doing work later this week. But the idea is that you can have total energy increase if there's something externally putting energy into the system. Right, number 4, so 2 identical objects are released from the top of 2 equally high, frictionless, so I don't have to worry about friction loss, and they are both the same height. Which box has a greater velocity at the end of the ramp? Well, if you look, so they both start with the same potential energy, and kinetic energy is 0 at the top because it says they were released, so it's not like they were thrown down, they were just dropped. So I have no motion, no velocity, no kinetic energy at the beginning, only potential energy. And because they're identical objects, so same mass, and they're the same height, they start with the same potential energy. And at the end of the ramp, that's going to be like on the ground, so UG would be 0. And assuming that it's frictionless, so they didn't lose any friction, that means they must have the same kinetic energy, because all of the potential at the beginning went into all kinetic. If this has the same all potential, then it has the same all kinetic. And if they're identical and they have the same kinetic energy, then they end with the same velocity. And it wouldn't matter if their masses were different, because we've done enough problems where you see the masses cancel out from height to velocity. So even if they weren't identical objects, they would still end with the same velocity. And the reason why is because they're starting with just potential, they're starting with the same height, and they're ending with 0 height, so that means all of that height went into its velocity. Which one reaches the end first? So they both end with the same velocity, but they do not go equally as fast the entire time. If you look, the one that would hit the ground first, like just gut instinct, you should say ramp 1, because it accelerates faster because it's steeper. So it's accelerating faster, so it gets to the bottom first. Now some of you are like, wait, but if this one accelerates faster, then how do they end at the same velocity? And my answer would be because ramp 2 has a slower acceleration, I'll say less acceleration, but for a longer distance and a longer time. So this one might not be accelerating quite as fast, but it does it for a longer distance and for a longer time, so it ends with the same speed. So they end with the exact same velocity, but this one got there first because it accelerated to that velocity first. And the last one I'll leave you to try on your own. You can check with Gabe.